So, I hope Tom gave you a clear picture of the capabilities of the solar electric vehicle. The solar electric vehicle could give the user clear advantages by using less energy. However, it could also be of great advantage to society. I will tell you how in the coming minutes. As you might have noticed, the energy system is currently subject to change. To limit climate change, a decrease in greenhouse gases is needed. Therefore, there is an ongoing electrification of the fossil-fueled power devices. One of those is the electric car. The future of cars is known to be electric, as world leaders are planning to phase out fossil-fueled cars from 2030. Have you ever wondered where all this electricity must be coming from? Well, the answer is the charging infrastructure and the electricity supply system need to ensure that every electric car is assured of an energy source in the future. However, they currently both lack capacity to do so. The charging infrastructure needs to pace with the fast-growing number of electric vehicles. As you can see, the current development of the charging infrastructure capacity is stagnating, while the number of battery electric vehicles is rising. There is need for a massive rollout of the charging infrastructure. However, placing public charging stations comes with costs. The second problem concerns the lack of the capacity of the grid. To show you how this works, we zoom into the local grid. The local grid is the final stage of the electricity supply system, supplying the electricity to your household or the supermarket. Together, households and shops have an electricity demand, which is schematically illustrated here. The capacity of the grid needs to be able to always deal with the peak electricity demand. Therefore, the historical designed grid capacity is based on the peak loads of the households. When the electric vehicle enters the system, the electricity demand curve and the peaks in the load curve increase considerably. The electric vehicle could double or even triple the peaks in the load curve. Well, this results in that the required grid capacity is higher than the current grid capacity. To ensure electricity access for everyone in the future, we need to reinforce the grid, replacing transformers and cables, bringing costs to the system. But what if I tell you that the cost for the grid and the charging infrastructure could be limited? The Lightyear 1, which Tom already presented, has generally a lower energy consumption than battery electric vehicles and has moreover an integrated solar roof in its body. Therefore, the solar electric vehicle needs to charge less, enabling a decrease in the required system capacity. But how much could the solar electric vehicle unburden the electricity supply system compared to the standard electric vehicle? And how many system costs could be saved? To determine this, we need to know roughly two things. First, the current level of the grid and charging infrastructure capacity, and second, the future energy demand to find out if the current level is sufficient. So, we needed to determine the energy demand in the future. But how do you do this? I will explain you how we did that. How much do you drive on a day? Well, the answer is directly correlated with your preferred energy need, right? But how much does your neighbor drive? When do you both decide to plug in your car? This could be totally different. The energy demand is largely determined by individual behavior. Therefore, it was found that we needed a bottom-up model, considering first the individual driving behavior to determine the energy needs of a total neighborhood. So, we modeled the energy system by an agent-based model, which allows simulation of behavior in order to determine the total system behavior. Well, after modeling the load curve, we concluded on two load curves in 2015. One for 100% battery electric vehicle adoption and one for 100% solar electric vehicle adoption, considering the driving behavior of different people in the system. We also modeled some additional electrification development, such as the arrival of the heat pump and electric cooking in the future energy system. The results were the two load curves that are shown. Next, the dump charging system in which people charge at the moment they want, we wanted to look into another interesting development, which is smart charging. Smart charging means that electric cars are incentivized to charge at optimal times, not during peak hours. Therefore, it has the potential to limit the peak loads of the neighborhood demand curve. I will show you how this works. On the screen, you can see a situation where no smart charging strategy is applied. The charging load adds up to the peak loads of the existing load. When implementing the smart charging strategy, the load is more distributed over the day. This limits the peak loads and is considered as a promising solution to prevent already a big part of the grid reinforcements. As smart charging is a very promising low-key solution that could be balanced and shift the load over the day, we assumed that this would be implemented in 2050. The model experiments were run in the most extreme conditions, in a winter week showing the highest peaks in the load curve and the highest maximum charging simultaneity. Moreover, the experiments were run for 3 different neighborhoods, distinguishing between 3 real urban, suburban and rural neighborhoods in Limburg. Based on this curve, the existing capacity of the grid and the charging infrastructure, we could derive the extra capacity needed in 2050 and the belonging costs. It was found that a total cost saving of €8 billion could be realized when massively adopting the solar electric vehicle in the Dutch society. The costs for the charging infrastructure in the battery electric vehicle scenario are €12 billion, and for the solar electric vehicle are €4 billion. This is 3 times less, which corresponds to the 3 times lower charging requirement of the solar electric vehicle. For the grid cost, no difference in cost was noted due to the load balancing mechanism in smart charging. In conclusion, we noted that for the grid infrastructure, no cost difference was noted. This was caused by the smart charging algorithm distributing the peaks over the day. For the charging infrastructure, there was a big difference in cost of 8 billion, of which the onboard solar generation accounted for 1/3 of the cost savings, and the other 2/3 was caused by the lower energy consumption of the solar electric vehicle.
Now that we know what solar electric vehicles are and the impact on the energy system is explained, let us dive deeper into some very interesting policy implications. Remember this slide? As explained earlier, a solar electric vehicle is radically different from forms of transport that we already know. Therefore, to be able to build legislation for such vehicles, a clear definition of what the solar electric vehicle actually is needed. Together with the Alliance for Solar Mobility, in short ASOM, we have proposed a factor to define a solar electric vehicle. As shown here, we can use the concept of energy consumption and energy generation again. Energy consumption of vehicles is currently measured worldwide by the WLTP, which stands for Worldwide Harmonized Vehicle Test Procedure. The energy generation can be determined by the Solar Standard Test Condition, in short STC, again a worldwide accepted standard. When you divide the energy generation by the energy usage, you arrive at a factor, which basically stands for the amount of solar kilometers which can be driven, and therefore by how much the charging frequency can be reduced. So this factor can be used to define when an electric vehicle becomes a solar electric vehicle. Now take some examples. There are some solar electric vehicles coming to the market already this decade. Besides Lightyear, we have a solar EV factor of 14. We expect the Aptera with a factor of 15 and Sono Motors with a factor 8 to be introduced. A very interesting side effect of this factor is that governments can, over time, push the industry by increasing the factor when technology advances. For example, when solar panels will become more efficient, the SEV factor could be increased as well. So, to summarize, we should adopt the SEV factor, determine a cutoff point, and keep track of the technology developments to increase this factor over time. When the definition is in place, policy measures can then be introduced to make use of solar electric vehicles and stimulate the use of solar electric vehicles. So all in all, I hope you enjoyed watching this video. If you want to know more about Lightyear, do not hesitate to contact me or Geert and Nienke. Also, we are always looking for ambitious students to join our mission. I hope to see you soon.